Mean value theorem. So police officers use a variety of techniques to assess drivers' speed and issue speeding tickets. Many people have tried to argue in court that these devices are unreliable. Does calculus have any answers for this? So Leanne is driving east on Reagan Memorial Tollway in Illinois. 2 weeks later, she receives a speeding ticket in the mail and the printout of her E-ZPass records. Looking at this chart, how many hours did it take Leanne to make it from Rock Falls to Maple Park? Well, it took her 48 minutes. So how do we convert that to hours? We just use our conversion. When we do this math, we're going to get that it took her 0.8 hours. So what was her average speed between Rock Falls and Maple Park? Remember, her average speed is just going to be the change in her distance over the change in her time. So go ahead and pause the video and see if you can find her average speed. Distance was 55 miles. Her time was 0.8 hours. You put this into your calculator, you're going to get that she was going 68.75 miles per hour. So if the speed limit was 70 miles per hour, is it possible that Leanne was speeding during that time period? Well, sure, it's possible. Her average speed was only 68 miles per hour, but she could have gone faster or slower at any various time on her trip. Then do the police officers have convincing evidence from the E-ZPass alone that Leanne was speeding somewhere between Rock Falls and Maple Park? Well, no, we can't be sure. She could have had her cruise control on for a constant rate the whole time. She could have been going a steady, constant 68.75 miles per hour. Then let's look at a different section of her journey. How many hours did it take Leanne to get from Maple Park Plaza to Elmhurst Plaza? Go ahead and do the same thing here that we did up in number 1. So go ahead and pause the video and go ahead and do that. So it took her 0.483 hours. And so now again, do the same thing in number 2 for number 6. What was her average speed between Maple Park and Elmhurst? Well, this time her average speed was 82.75 miles per hour. So this time, do police officers have convincing evidence from the E-ZPass alone that Leanne was speeding somewhere between Maple Park and Elmhurst? And how do you know? And so, of course, yes, since distance is continuous, if her average speed was 82.7 miles per hour, at some point she had to go above 70 miles per hour. Then also, must there have been a moment when Leanne was driving exactly her average speed, and how do you know? Well, yes, of course there was. In fact, there was a time that she was driving every single speed between 0 and at least her average speed. She couldn't just skip over that average speed, so there was in fact probably a time that she was driving above that average speed. Then what is the mean value theorem? It states that if a function f of x is continuous on the closed interval a to b, and differentiable on the same but open interval a to b, then there exists a value c that's between a and b such that f prime of c, the instantaneous rate of change, equals basically the slope formula, the average rate of change. Let's take a look at what this looks like graphically. So there I have a function that is continuous and differentiable on the interval from a to b, and there's a value c between a and b. And when I find the average rate of change between a and b, it's equal to the instantaneous rate of change, or the slope, at c. And that's what it looks like graphically. One way that we can prove or use the mean value theorem, first of all, we would have to make sure that the function is continuous and differentiable. Then we need to find the average rate of change on that interval. And we would also need to find the instantaneous rate of change, or the first derivative. And then we basically need to set those equal to 0 and solve for x. All right, let's do a couple of examples. Let f of x be a twice differentiable function such that f of 4 equals 7 and f of 7 equals 4. Show that there must be a value c that's between 4 and 7 such that f prime of c equals -1. Since f is differentiable, it is therefore also continuous, so we've met the condition of the mean value theorem. Therefore, there has to exist a value such that the first derivative equals the average rate of change. So we just need to prove that the average rate of change is what the given first derivative is, which is -1. So stop the video and go ahead and find that average rate of change. The average rate of change is just the slope, so the y minus y over x minus x. So we get 4 minus 7 over 3. And when we simplify this, we do in fact get -1. Number 2, a test plane flies in a straight line with a positive velocity v of t in miles per minute at time t minutes, where v is a differentiable function of t. Selected values of v of t are shown in the table below. Based on the values in the table, what is the smallest number of instances at which the acceleration of the plane could equal 0 on the open interval from 0 to 40? Since it's the velocity function that's given, we need to find the number of times that the acceleration, or the first derivative, could equal 0. So are there any intervals in which the velocity would have an average rate of change of 0? And we can see, since my y is the same there, the average rate of change would be 0 there. And again, from 25 to 30, the average rate of change is 0. So those would be the two instances that the acceleration by the mean value theorem are guaranteed to be 0. And finally, the graph of g of x is shown below. Find the average rate of change of g of x over the interval from -3 to 7. So basically we want to find what's the average rate of change, what's the slope of that line from -3 to 7. So go ahead and pause the video and do that. And you should have gotten 1/2. Part B, does the mean value theorem applied on the interval from -3 to 7 guarantee a value of c in that interval such that g of x is equal to this average rate of change? No, it doesn't. And why doesn't it? The mean value theorem doesn't apply here because g of x is not differentiable on all values of x in that interval. Once again, remember that for a function to be differentiable, it has to have the same slope as the value is approaching x from both the left and the right. So this is not a differentiable function, continuous differentiable function. If you have any questions, please bring them to class.